voltage at the output, the DC voltage at the output, if we assume the input is 0, so we kill the input, and we want to find out the voltage at the output due to just the input current. So V out, okay, is equal to the I minus. Okay, let's do I minus first. When we're dealing with I minus, we kill I plus, we kill Vs, and therefore there is no current flowing through this 50 ohm. The voltage here is 0. And since the voltage here is 0, the voltage here is also 0, virtual ground. And therefore, I minus flows through the 500K. So you have I minus, which is 1 micro, flowing through 500K. And that now appears at the output. I'm not going to use the I plus times R2 anymore. I just immediately put in the values. Okay. Then I look at I plus. So I plus is flowing out from ground. All right. As it flows out from ground, it incurs a negative value there because the voltage is more negative than ground at the non-inverting input. So minus I plus is again 1 micro as well, multiplied by 50 ohm. All right. And then at this point it goes out, we multiply by 11 non-inverting gain. Right? Is it okay? Alright, so this is the result, and you get 499.45 millivolt. Okay? So this is the DC voltage at the output due to I plus and I minus. So then in part 2 of this question, which is question 6 of tutorial 2, right? We are told that we want to add an additional resistor in series with this 50 ohm. Right? So we're going to put in R additional. We're going to add in an R additional in series with the 50 ohm such that the output, the DC output becomes 0. So now the new V out now is 1 micro multiplied by 500K, no change, right? Minus 1 micro, still the same current, 50 ohm plus R additional. We add in an additional resistor in series times 11, which is your gain, right? So now we want to find out this by equating this to 0 because we want the minimum DC voltage at the output. So the minimum will be 0. So therefore, we equate this. Now since this is a positive term, this is a negative term, what chance? What chance to make it 0, right? So that's why we can do it. So we end up having R additional is equal to 1 micro times 500K, right? And then divide by 11, divide by 1, okay, minus 50 ohm. Right? And if you work this out, this will be equal to 45.4 k ohm. Okay? Alternatively, R at plus 50 ohm must be equal to R1 in parallel with R2. Okay? If and only if I plus is equal to I minus. Right? So in this case, R at is equal to which is 50K in parallel with 500K minus 50 ohm. Right? This will similarly give you this answer. How come? Because this thing is Rx in the lecture note. Remember we did Rx in the lecture note. We say that, okay, when we look out from the positive or the negative terminal, when we look out, we are expected to see R1 and R2 in parallel, right? So that value is Rx, right? So when the two current is the same, I plus and I minus the same, we can cancel out the DC offset due to these two current if they are the same by inserting a resistor at the non-inverting terminal of the value equal to R1 in parallel R2. Okay? All right? Okay, let's move on to question 7 of tutorial 2. So in question 7, we're told that we have the cascading amplifier again. Again, the gain is 20 in each of the stage, right? So again, this is 20R, this R, 20R, this R, and this is the input, this is the output. And there is no offset in this case. But in this case, the output rail is capped at 14.3 and minus 14 volt. DC is 0 because there is no offset, no bias current, no nothing. So the output is at 0. So we are asked to find out the maximum input frequency, maximum input amplitude, in which it will lie in a linear range. So in this case, this is again plus minus 15 volt, but the output swing now lies within the linear range of 14.3 and minus 14. So when the output swing, which the maximum amplitude that goes undistorted will be 14 volt. Why? Because 14, the magnitude of 14 is smaller than the magnitude of 14.3, right? So it will hit minus 14 first. So if you increase the input frequency, input magnitude too large, although it will hit 14.3 nicely, but by the time it hit the negative rail, it will be clipped on this side. So the maximum amplitude we can have is 14 minus. So therefore we can write that the output is equal to the input multiplied by the two inverting gain, which total up to be 400. Right? So therefore we can find out the input signal. Since we know the output will be maximized at 14 volt. So the input will be V in, right, with 400 gain, and therefore V in is equal to 14 divided by 400, and that is 35 millivolt. Right? So V in would have a peak value of 35 millivolt. If we want to write the equation, the signal properly is 35 millivolt sine omega t or cos omega t, whichever. So this is your input signal. Then we were asked to find out what is the maximum frequency that can go through this amplifier coming out undistorted if given that the slew rate is 1 volt per microsecond. So if it is 1 volt per microsecond, this value must be greater or equal to the maximum rate of change at the output. Right? So, but what is dV out dt? So dV out dt is equal to this gain multiplied by the input frequency. And of course you dt the whole thing, because I haven't differentiated. So this becomes 14, okay, omega cos omega t, the one to know the sign, don't remember. Okay, so that is what we have, And to find out the maximum value, we know that the slew rate, which is 1 megavolt per second, must be greater or equal to the maximum rate of change of this, which is 14 omega, max. Right, so therefore we can find out frequency F max. F max will be smaller or equal to 10 to the 6 divided by 14 divided by 2 divided by pi. Right? Oh, 2 pi F is equal to omega, so I can bring the 2 pi below. Oh, okay. Right, so I end up with this. And if I work this out, this is equal to 11.4 kHz. So the frequency must be smaller than this value. The maximum frequency must be smaller or equal to this value. Anything bigger than this, the output will go out distorted. Okay? Any question? Is it clear? Okay? Then we take a look at tutorial 3. Okay, let's look at tutorial 3. So in tutorial 3, we have this question. We are told that the op-amp has a unity gain frequency of 1.2 meg, and the op-amp is configured this way. All right, it's a non-inverting amplifier with a gain of 19/5 plus 1, which is 20. Right, and we want to find out the closed loop bandwidth of this. Right, so to find out the closed loop bandwidth of this, we know that this graph ends at this point, which is 1.2 meg. And this here is Fp, this is F0, and this is A0. And every time we close the loop, this would be 1 over beta. Right? This would be 1 over beta, where beta is the feedback factor. And this here would be your closed loop bandwidth. Right? In other words, A0 times Fp is also equal to 1 over beta times the closed loop bandwidth is also equal to F0. This is the gain bandwidth product. Right? The gain bandwidth product. And in this particular case, we are told what is the value of F0? 1.2 meg. And we also told that the gain of this amplifier is 20, because you have 95 here, and this is 5, and we are entering from the non-inverting input, and therefore 1 over beta is equal to 20. Right? And therefore we can write this equation as, or rather 20 times the closed loop bandwidth is equal to 1.2 meg. And therefore the closed loop bandwidth is equal to 1.2 meg divided by 20, and this is 660K. Okay. Then we look at part B. So this is part A. So in part B, we are told that the closed loop gain, we want to find out the closed loop gain when the bandwidth is now at 600K. So we now have a bandwidth that is 600K. So we don't know this gain now, but we know this bandwidth, and everything still ends up to be F0. So 1.2 meg is equal to 1 over beta times the new bandwidth, which is 600K. So 1 over beta will be 1.2 meg over 600K, and this is 2. Graphically, this would be, let's say we look at this, let's say this is a gain of 20, so this is at a gain of 20, right? And at this point, this is 60K. So if we shift to 600K, is 600K, right? Then this is 1 decade. From 60K to 600K is 1 decade. That slope is supposed to be 20 dB per decade. Alright, so that means to say 20 dB drop. From here it drops to here, there is a 20 dB drop. 20 dB drop, if you convert 20 dB back to non-dB, is 10 times lower. So if this is 20, if I divide it by 10, I will get 2. Alright, don't do this. If you don't understand, don't do this. This one is just for your understanding if you look into dB. Alright? Okay? So the gain is 2. Alright? Forget what I say, the last few statements. Erase from memory. Okay? Don't bother. Not now. Wait until the last portion of this part 3. You'll deal into dB. Right? At the moment, there's no necessity for dB. Okay? So this is question 1. Right? So let's take at 1B. Right? In 1B, we are given this op-amp. 20K, 20K, goes to ground, input at the non-inverting input, and the signal looks like this. Goes from -2, it goes up, all the way to 5 volt, and it flattens out, and at this point is 5 microseconds, and this here is at 4 volt, is it? No, 5 volt, sorry. Okay. So, if you look at the gain is 1 plus 20K over 20K, so it's 2. The gain is 2. Right? So therefore, if I input this signal, this is V in, then V out would be multiplied by 2. You start at -4 volt. By the time it goes through, it will go through 0, because when the input is 0, the output is 0. So it will go through 0. And it will proceed to go on. When the input is 5 volt, the output will be 10 volt. So it's somewhere here. And this guy will go all the way to this. And then you will flatten out again. And this is at 10 volt. This is your V out. Not so good. Okay. So this is your V out. This is your V in. So you want to find out whether this output will it be distorted or not. So we know that the op-amp has a slew rate, in this case, of 4 volts per microsecond. And we need to know that the slew rate must be greater or equal to the maximum rate of change at the output. And the maximum rate of change at the output is 10, this is 10 volt, minus -4 divided by 5 microseconds. And that works out to be 2.8 volt per microsecond. So, is the slew rate, which is 4 volt per microsecond, larger than the maximum rate of change at the output? Yes, no, none of the above. Yes, right? It is indeed, this is indeed larger than this. So therefore the output goes through undistorted. Okay? Okay? Yes, no, none of the above. Does that remind you of something? Yes. 22nd of February. I keep reminding you all of something. Right? 22nd of February, what is it? It's a big day, you know. Because you all have to come back on a Saturday afternoon. Okay? Alright, so this is 1B. Alright. Let's look at question 2. So in question 2, we are given an op-amp. There is 33K here, 10K here, input going into the inverting node, right? And we are told that there are 4 different signals coming in. And the 4 signal is V1, V2, V3, V4. Each of them has different amplitude and different frequency. The first one is 0.01, second one is 0.05, third one is 0.1, fourth one is 0.2. They are all sine wave, alright? And each of them has different frequency, angular frequency. This is 10 to the 6 T. This is 350K T, alright? And this is 200K T again, alright? But I shouldn't be using the K, but I play cheat a bit, because otherwise too many numbers there. So I shouldn't be writing the K there. It should be written as 10 to the power of plus 3. But I play cheat a bit, because if you put KT, it sounds like Bowman constant and the temperature. So don't do that. I can do it because I'm explaining why I did it. Okay? But don't follow me. So here, this is what we are entering to the amplifier. And the output, we're going to get V out given by the input amplitude, AN, okay, input amplitude, multiplied by the closed loop gain, multiplied by the signal that comes out, sine omega t. So this would be at the output. Alright, so we know that the slew rate must be greater or equal to the maximum rate of change at the output of this signal. So this, we want this to be the maximum. Alright. So if we look at this, what is dV out dt? dV out dt will be the amplitude, alright, times the closed loop gain. Goes into cos omega t with a omega in front. Okay, forget about the sign. Not interested with the sign, right? So I magnitude it, and we know that the slew rate must be greater or equal to the maximum of this. So this maximum is when this is omega max, am close to gain. Okay, cos omega t becomes 1. Right? So this is the formula that we end up deriving. Right? So now let's take a look at for the 4 signal. Right? So we want to know what is the maximum frequency for each of them. So omega max will be smaller or equal, must be smaller or equal to the slew rate divided by the input amplitude divided by the closed loop gain of the amplifier. So for the first signal, this value must be smaller or equal to the slew rate is given to be what's that value? 5 volts per microsecond. I mean 0.5 volts per microsecond. So we can now put 0.5 times 10 to the 6, that makes it megavolt, divided by the input amplitude of the first signal, 0.01, divided by the closed loop gain, which is 33. And if you work this out, this frequency is found to be What's the value? It's found to be 1.515 times 10 to the 6. Right? So if you look at this, the input frequency that we are entering is 1 meg. All right? But the maximum allowable frequency is 1.5 meg. So therefore, the first signal goes in the amplifier, comes out undistorted. So it's good, no problem. All right. Let's look at omega max for V2. 0.5 times 10 to the 6 divided by 0.05 times 33, same thing. Work this out. It is 303.03 times 10 to the 3. Yeah? So if you look at the second signal entering is 350K, but the maximum permissible frequency is 303K. So that means that value is much higher than the maximum allowable. And therefore, it will go out distorted. It will go out distorted. Then we look at the third one. Okay. And again, if you look at it, the input is 200K, the maximum allowable is 151K. So again, it goes out distorted. All right. Then we look at the fourth one. Again, same value, except for the amplitude that changed. Now this one is 0.02. Right. Multiply by 3, this one will give you 75.75K. And we are entering the signal that is at 50K, smaller than the maximum. Smaller than the maximum. And therefore this goes out undistorted. Okay? So this is just to show you what is the maximum allowable and whether the input frequency is beyond or below. All right. If it is below, no problem. If it is above this value, then it will go out distorted. All right. And if you heard my lecture this morning, were you in class this morning? Same group? Yes? No? Yes? No? No? No. So I will do that on Friday then. I introduced a simulator. And with the simulator, you can change some of these parameters and see the distortion in the waveform and all that. So you can do that by doing some simulation. All right? So now let's take a look at this same equation now. If we look at this equation, we see that if we want to make any change to this op-amp configuration, such that we do not need to change the input frequency. The force signal still has to come in. We don't want the force signal to go out distorted. Then what must we do? So we look at this equation. That means to say we have to maintain the amplitude. We have to maintain the input frequency. So we have only these two terms to play. Right? We have only these two terms. We can either change the slew rate or we can change the gain. Right? If we choose to change the slew rate, we end up changing the op-amp. That is costly. If we change the gain, we just change the resistor value, and that sounds a lot cheaper. So therefore, we can have the two alternatives. Let's look at the values that we need to get done with. Right. So here again, we look at this formula that we have derived. This slew rate must be smaller or equal to, or rather slew rate must be greater or equal to the maximum angular frequency times the input amplitude times the closed loop bandwidth. Right? So for the first frequency, if we want to find out the slew rate that is required for the second signal, because this is the one that is distorted. So this must be greater than the maximum permissible frequency that is entering this. Now this frequency is 350K, so we put 350K here. The input amplitude is 0.5. Closed loop gain is 33. So if you work this out, this is 0.5775 volt per microsecond. Alright. And then if you look at the slew rate required for the third signal, because this is also going out distorted, we pump in the frequency that is about 200K. Alright. The input amplitude is 0.1. Multiplied by the same gain, and if we work this out, this is 0.66 volt per microsecond. So in order for all the four signals to go through undistorted, we will change the slew rate of the op-amp to the bigger one. Because with the bigger one, it will include the second signal as well. So all four signals will go through undistorted. But if you go and buy an op-amp, if you go and ask the person that sells the op-amp, I want an op-amp that is 0.66 volt per microsecond, the person will say, you're going to find someone else to buy. I can't give you specifically this value. But he can say that, okay, I'll give you an op-amp that is 1 volt per microsecond. And that is good, because it will clear almost everything. Alright? Alright, so you can choose any op-amp with a slew rate that is higher than that. Okay? What about gain? So using the same equation, you can bring out the gain, and therefore the gain must be smaller or equal to the slew rate divided by the maximum frequency permissible, or rather the maximum frequency that is being used by the four signals, alright, and then the amplitude as well. So for the gain that is required for the third signal or the second signal, it must be smaller than 0.5 times 10 to the 6 divided by the frequency, which is 350K, or rather times 10 to the multiplied by the input amplitude, which is 0.05, and this works out to be 28.57. Alright, and for the gain that is required for the third signal must be smaller than 0.5 times 10 to the 6 divided by 200K times the input amplitude of 0.1, and that works out to be 25. So if you look at this two again, you would use the second gain. With the second gain, you will be able to accommodate all the four signals, inclusive of the second one. So therefore, all you need is to change the resistor, and in this case, we can change the resistor so that the amplifier looks like this. $250K, 10K, and you'll be able to get a gain of 25. Right? Instead of 330K, now you swap it to 250K. Then all four signals will come in and go out undistorted with the gain of 25. Okay? Any question? Any question? Okay. So that is question number 2. So let's look at question number 3. So in question number 3, we have a signal that comes in that looks like this. All right, and this is volt. This is time, and this is about 4 volt. This is about 6 volt. This is minus 3 volt, and this occurs at 2 microseconds. This at 10, and this is at 16. No, this is at 12. This is at 16. This is at 18 micro. All right, and we are told that the op-amp is this. we asked to find out what is the minimum slew rate that is required by this op-amp, alright, such that this signal goes in and comes out undistorted. So therefore, in order to find out this slew rate of this op-amp, we need to know that the slew rate must be greater or equal to the maximum rate of change at the output. So what is the maximum change at the output? What is the maximum rate of change at the output of this signal? It would occur at this portion, correct? And therefore, this will be equal to 6 divided by 2 microwatt, and this is 3 volt per microsecond. So the minimum slew rate that is required is 3 volt per microsecond. Alright, because it occurs at the last portion of this waveform. That is the steepest part, correct? Hello. Capito? That is Italian for understand. Okay? Of course, if you don't understand, you say non capito. Oh, okay. So now, if you now change the op-amp configuration such that we put a resistor here and another resistor here, and this becomes a non-inverting gain amplifier. And this time it says that the gain is introduced by having a 50K and a 100K. So this is a 100K and this is a 50K. And therefore this gain now is 3. Right? The new gain is 3. Right? So therefore the output waveform would look like this. This will go all the way to 12. Right? It will go through the same zero crossing, because when it's 0, the output is also 0. And it goes down to -9, flats out, goes through the same zero crossing, and then it goes all the way to 18, and then it drops back to 0. Okay, so this is your output waveform. So, in order for this signal to go through undistorted, what is the maximum rate of change? Same portion. It will be the same portion. Therefore, the slew rate that is required for this op-amp must be greater or equal to 18 divided by 2 micro, which is 9 volt per microsecond. Right? So for the second part, the required slew rate must be at least 9 volt per microsecond. Okay? So this is very simple. Any question? So let's look at the last one. Okay, in the last one, we are given a black box, and we are told that we're going to enter a signal with an input resistor that is 600K or 60K, and the source, okay, is a 1 volt RMS. Okay, and at the output is driving a load. And this load is 1 k ohm, and the output is at 2.5 volt RMS. Okay, so this is ABCD. Okay, so we're gonna replace what is in this black box. We're going to design whatever is in the black box. Alright, so let's take a look at what are the possibilities here. So here we are told of one condition, that the phase at the load is of no concern. That means to say whether it is inverted signal or non-inverted doesn't matter. We don't care about the phase. So therefore we can first do this. So this is your B, this is your A, this is your C, this is your D. Okay? And here we can put 40K, this is 250K, and we would have a gain that is 2.5 because your gain supposed to be 2.5 because the input is 1, the output is 2.5. This is what you want, and this is given by 250K divided by 40K plus 60K. Right? Forget about the phase. This is a non-inverting amplifier. The gain would be R2 over R1, but R1 is a summation of this 60K with the input resistor that we have drawn 40K. All right? Together, it will give you a gain of 2.5. Am I right? Okay. So we could do this. Of course, the selection of the resistor is very limited because of the fact that you have this 60K here. Right? Because of this 60K, we have a limited choice of resistor. We could remove the 40K. If we remove the 40K, then the 60K becomes the resistor that is connected to the inverting input. And therefore this resistor becomes 150K because 2.5 times of 60. Right? So again, if you look at it, the selection of the resistor is very limited. By the way, this is a minus here. Alright, it's very limited because we have a source resistor connected to it already. Therefore, the limitation is fixed by that. Alright, so limited choice. We could also have B. In B, we could do this. And this here would be R2 over R1 must be 2.5. Right? R1 over R2 ratio is 2.5. Here, as long as the ratio is 2.5, you can use it. Alright? So you have a huge range of selection for resistor. Only problem is you need 2 op amp. Alright, so the cost becomes a big problem here, right? So not a good choice because you end up paying for 2 op amp, alright? You're paying for 2 op amp just to increase your selectivity range of your resistor. So that is not a good choice, right? So let's take a look at the third one. So the third one, of course, would be the best. Okay, it is R2, R1, and R2 over R1 is equal to 1.5. Okay, so now this one uses only 1 op amp and a huge selection of resistor as long as the ratio is 1.5. Right? You can have a huge selection of ratio that gives you 1.5. Right? But the only thing, the gain is of course 1.5 instead of 2.5 because of the fact that this is a non-inverting amplifier. So you have 1 plus R2 over R1 having 2.5, right? So therefore this selection is this. So out of these three, which would be your best choice? obviously C. Why? Because C uses only one op-amp. You have a huge selection of resistors that you can choose from. Right? If you choose B, your boss is going to kill you because you are spending in excess. You choose A, you have very limited choice in the resistor value that you can use, and therefore certain range of your resistor is overly used, whereas the other range are not being used. Okay? Alright, that's it.